Before I get started today, I have a question for you all. What is the world's largest man-made thing? Any ideas? Well, the correct answer is actually the Great Pacific Garbage Patch, with a surface area of 1.6 million square kilometers. That's nearly 6 times the size of New Zealand, made up of 80,000 tons of plastic. According to Plastics New Zealand, each New Zealander consumes approximately 31 kilograms of plastic packaging every single year, and only recycles 5.58 kilograms. Plastic accounts for around 8% of New Zealand's waste by weight. However, because plastic is so light, it's estimated it's as much as 20% of our landfill space. Around 252,000 tons of plastic heads to our landfills every year. So what currently happens to plastic in the ocean? Larger plastics like plastic bottles and packaging are broken down from sunlight, oxidation, friction, and animals nibbling away on the plastic. This process continues for smaller plastics until the plastic is now nanoplastics. These nanoplastics cannot be fully removed from the environment and are extremely harmful to marine life. This process can take up to 500 years for plastic bottles. Even though the plastic has been broken down, it still exists in a harmful form as nanoplastics. Okay. So it's quite clear that plastic that ends up in our landfills or in the ocean can have significant environmental effects, even when it is broken down. What about plastic, or more specifically, polyethylene terephthalate, PET, that is recycled? Firstly, the plastic is shredded into smaller pieces, making it easier to clean and process. The plastic bits will then be washed and cleaned in order to remove labels, glue, and residue. Next, the plastic pieces are grinded up into small flakes. At this stage, the smaller flakes, called rPET, or recycled plastic flakes. These recycled flakes are then tested and made into new plastic items. Note that this process isn't particularly profitable, and only a small proportion of plastic can even be recycled this way. Furthermore, in countries like New Zealand, labor is so expensive that it can't even be done here. Clearly, we need a better solution, one that is more sustainable, one that is more thorough, and one that is more reliable. Polyethylene terephthalate, or PET, is the most common type of plastic, and it is a polymer, a long chain of monomer building blocks. PET biodegradation is an up-and-coming field where scientists are trying to find and build enzymes that can efficiently break down these polymers back into their monomer building blocks. This process is called depolymerization, and when we can find an efficient and cheap way to do this, we can say goodbye to plastic waste forever, as we can simply depolymerize used plastics and turn them into any other plastic thing we like. In 2016, several Japanese scientists discovered a bacteria named Ideonella sacchariniensis 201F6 in a plastic recycling facility, nibbling away at the delicious PET. The bacteria uses the 2-enzyme system to depolymerize PET, PET hydrolase and MHET hydrolase, also known as PETase and MHETase. Essentially, the bacteria utilizes PETase to break down PET into BHET, MHET, and TPA. Then, the PETase further breaks down the BHET into MHET and EG. Finally, the MHET is broken down into TPA and EG. TPA and EG happen to be the monomer building blocks for PET. From there, we can just take the products and make whatever we want with it. Okay, so that's the plastic enzymes part of Mutant Plastic Ninja Enzymes. Let's talk about the mutant part now. Scientists have found a way to modify the structure of PETase to make it more efficient. By narrowing the binding cleft of the enzyme, or the active site, PETase takes just a few days to break down the PET, as compared to the 100 of years in oceans. This is great. Furthermore, scientists have found a way to make super enzyme chains. By stitching together PETase and MHETase enzymes, we can again increase the efficiency of the PET degradation. Interestingly, just last year, scientists discovered another enzyme with similar action that was able to break down PET in just 10 hours at 72 degrees Celsius, which is very close to the melting point of PET. This is an incredible advancement and is already being trialed in industry. I just want to end by talking about an important perspective in this conversation about strategies to protect the environment. Firstly, this solution acknowledges the fact that we are tightly interconnected with nature. The fact that a seemingly random bacteria is capable of recycling and digesting this pernicious polymer that humans have created represents this. Inspired by nature, we're able to harness the power of naturally occurring organisms to help us solve the problems that we've created. Secondly, this solution is sustainable. By using these enzymes to recycle PET polymers, we can one day achieve our dream of a plastic waste-free future. It's not completely viable to abolish plastic altogether, but this technology just means that plastic is no longer considered permanent waste.